Okay, we're going to talk about properties of ionic compounds and covalent compounds. At the end of the screencast, you should be able to identify a compound as either being ionic or covalent based on its properties. And you should be able to explain, and this is perhaps the harder part, explain those properties of a compound based on its bonding or on attractive forces that are present. So, big idea, right? So why are there different properties for ionic and covalent compounds? The big idea overview. Structure of a compound is going to dictate its properties. So how the elements, these atoms, ions are put together in a compound really dictate what kind of properties it's going to have. And that structure of a compound is going to be related to the bonding that is present between either those atoms or ions, or we're going to write this, the attractive forces between particles. So that's going to cover some attractive forces that are not necessarily the bonds between those atoms. Here is a chart that summarizes some of the properties of the compound. Okay. Soluble in water. Ionic compounds are usually soluble in water, some are not. Covalent compounds, sometimes. Okay, when you talk about covalent compounds, it's a wide range of things, anything from gasoline and oil to sugar to wax. So there's a wide range of covalent compounds. Can we conduct electricity as a pure substance? Ionic compounds, no. And remember, we'll define conductivity in just a moment. Okay, covalent compounds typically no. There are some exceptions, but typically no. They do not conduct as a pure substance. Do they conduct when they are dissolved? Ionic compounds, yes. Covalent compounds, usually not. All right, so for this unit, because we'll get to these exceptions in a future unit, the answer to these questions are: conducts as a pure substance, covalent, no. Conducts when dissolved, you can say usually not. I would answer no if I'm given a yes or no possibility. Do these substances conduct when melted? Ionic compounds, yes. Covalent compounds, no. What would their melting points be generally? And this is generally. Ionic compounds typically have high melting points, so they are typically solids at room temperatures and pressures. Covalent compounds can have a low, can have a medium, can sometimes have a high melting point. So they can be either solids, liquids, or gases at room temperatures and pressures. Temperature, room temperature is taken to be 25 degrees Celsius, pressure 1 atmosphere. Now let's look a little bit more in detail of some of these things. Quick review of what we know so far about these bonding of ionic and covalent compounds. Remember, an ionic compound is a bond between a metal and a nonmetal. Metals have low electronegativity, meaning they don't hold their outside electrons very tightly to themselves. Nonmetals have high electronegativity, meaning they have an ability to attract a pair of electrons to themselves. The electronegativity difference is large between those two, which means that the electrons are transferred from the low electronegativity metal to the high electronegativity nonmetal. You can think of a little brother and a big mean brother, okay, that steals his candy. In a covalent compound, I have two nonmetals bonding. Each has a high electronegativity, but the difference in that electronegativity is small. So neither one of them really is able to grab the electrons from the other. These electrons then are shared, and you can think of twins. We'll find that these types of bonds dictate physical, chemical properties. We're going to focus more on the physical. Looking at these three pictures, you hopefully should be able to identify which one is covalent, ionic, and metallic. We'll start here because it says metallic. So this is a metal. Okay. These represent electrons, and these are free to move. Remember, metals have low electronegativity. They don't hold those outside electrons very tightly, so their valence electrons are able to actually move throughout the metal. I should say their outer electrons. When they lose these electrons because they can move, what you're left with is a positive inner core. Okay, so this is the positive inner core of a metal atom. That just means that the outside electrons are free to move, so I've got that positive thing in the center. Hopefully you can identify this as your ionic compound, okay, with your cations alternating with your anions. Cations being positively charged, anions being negatively charged. These lines represent my ionic bond, which is really just an electrostatic attractive force between oppositely charged particles. These are taken to be pretty strong. So those are a strong attractive force. Hopefully you identified this. It's actually water, so this is a covalent compound. Okay, and what we make here is molecules. By the way, the structure here is known as a crystalline structure, sometimes referred to as a lattice structure. So let's talk in detail about some properties that we're going to delve into deeper, why some things act certain ways. Conductivity. And in particular, we're going to be talking about electrical. And there is also thermal conductivity, which is the ability to transmit heat through a substance. Electrical conductivity is the ability to transmit electricity through a substance. In order for something to be conductive, I have to have the presence of charged particles, and those charged particles have to be free to move. Okay, so charged particles, and they have to be free to move. So mobile charged particles have to be present in the substance. Melting point. Melting point is the temperature at which a substance goes from a solid to a liquid. In order for something to go from a solid to a liquid, attractive forces between the particles have to be overcome by the movement or kinetic energy of those particles. As I warm up particles, as I heat them up, add energy, the kinetic energy increases, and to the point that that movement overcomes these attractive forces. If we look at a covalent compound, okay, the forces that have to be broken are these intermolecular forces. They are attractive forces between, in this case we're looking at water, between the hydrogen atom of one molecule and the oxygen atom of another. So for covalent compounds, we are breaking relatively weak intermolecular forces. Not the covalent bond. Okay, not. Do you think I'm stressing that? I am. Not the covalent bond. All right, so when we melt things, it's the attractive forces between molecules. All right, when we look at this ionic compound, in order to melt this, we have to break, that says break, believe it or not, break the ionic bonds. Which are strong attractive forces. A strong attractive force. Okay. Okay, so take a look at ionic compounds. What are ionic compounds made of? It's in the name. These are made of ions, charged particles, correct? Charged particles. So, ionic compounds have a high melting point. They're solids at room temperature, and again, to melt them, ionic bonds must be broken. That attraction is very strong. I don't know what that is. Okay. Ionic compounds conduct electricity in solution and when melted, because when they are in solution or melted, ions then are free to move. It does not conduct electricity as a solid because as a solid, these ions are locked into place by the strong ionic bonds. There are no mobile charged particles present. Are there charged particles present? Yes, but they're not mobile, so it will not conduct electricity as a solid. Hey, we get to watch a movie. Well, it's a little video clip. Don't get too excited. Here we go. Wait. Yeah.
Sodium chloride is placed in water. Water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay. The more important thing,
surface.
The more important thing to note here is not that it makes that what they call a hydration shell, but when we dissolve these particles, right, when water, salt is put in solution, I have now these ions that are free to move. Okay, that's the point that's being made there. That's not where I want to be. Oh. Okay, so I like that video clip though because I think it helps you visualize what's going on. And hopefully you can see too if I'm going to melt it. Maybe I should go back to it. Okay, if I melt it, what I'm doing is I'm breaking these attractive forces between them, and it would just, then they would be able to move. But when they're solid, these are locked in place by the ionic bonds. So how about covalent compounds and their properties? Covalent compounds tend to have lower melting points than ionic compounds. They can be a gas, a liquid, or a solid at room temperatures and pressures. And the reason is to melt a covalent compound, we are breaking the attractive forces between the molecules. Those attractive forces are typically weak compared to the covalent bonds. Okay, so here's a picture. This is the attractive force that is being broken so that these molecules still stay as molecules. I'm not breaking the covalent bond between atoms. I'm breaking this intermolecular force, forces between molecules. Okay, and those are rather weak. Typically, covalent compounds do not conduct electricity because a molecule, since there's been no transfer of electrons, only sharing, molecules are neutral. Okay, in a future unit, we'll see that there's an exception in acids, but we'll look at that in the future. For now, we're going to go with typically covalent compounds do not conduct electricity, even when they're melted or when they're dissolved in solution, because the molecules stay as molecules. Oh, nope, the movie's for this one. All right, so I wanted to throw in metals. It's not really part of this unit, but it's important, I think, for you to understand metals at least a little bit because they are an important part of our world. All right, so metallic bonding is often described as a sea of electrons moving through positive inner cores of metal atoms. Okay, so these are the inner core, these electrons move. Metals tend to have lower melting points than ionic compounds. They are typically, though, a solid at room temperatures. When you melt a metal, you are breaking the attractive forces between the free electrons and these inner core. Okay, the strength of those bonds depend both on the charge and how far apart they are, or how big that inner core is. Metals conduct electricity because these sea of electrons, remember they're negatively charged, are free to move. So I have those mobile charged particles because those electrons are free to move. I found a video, I think, that shows it pretty well, so I'll share that with you. Okay. So here we see a sample of the metal, all right? And there's a battery, and right now it's open, all right? So you see the metal, the electrons, which are the red dots, moving in random directions, okay? So they're just moving randomly in all directions. They're also called delocalized electrons, that sea of electrons. Then we should, there we go. Now we put the switch on and you can see that those electrons are moving towards the positive battery terminal. Okay, and we've just completed the circuit, so they just keep moving. But that gives you an idea of what a metal would look like if we were able to blow it up to that scale. And that ends this screencast.